Section 14 of the Chemistry of Cookery. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Charlie Newsom, Livingston, Montana. The Chemistry of Cookery by Mattieu Williams. Section 14. Vegetable Casein and Vegetable Juices. As most of my readers doubtless know, peas, beans, lentils, and other seeds of leguminous plants are more nutritious, theoretically, than the seeds of grasses, such as wheat, barley, oats, maize, etc. I was glad to see at the Health Exhibition a fine series of the South Kensington cases, displaying in the simplest and most demonstrative manner the approximate analysis of the chief materials of animal and vegetable food. I refer to them now because they did not receive the attention they deserve. On the opening day there was, out of all the crowd, only one other besides myself bestowing any attention upon them. These cases show 1 pound of wheat, oats, potatoes, peas, etc., etc., on trays. By the sides of these are bottles, containing the quantity of water in the 1 pound, and other trays, containing the other constituents of the same quantity, the starch, gluten, casein, the mineral matter, etc., thus displaying at a glance the nutritious value of each so far as chemical analysis can display it. Those Irishmen and others who think I have been too hard upon the potato will do well to take its nutritive measure thus, and compare it with that of other vegetable foods. I should add that these cases form a part of the permanent collection of the South Kensington Museum, and therefore may be studied at any time. All the leguminous seeds, the groundnuts, etc., have their nitrogenous constituents displayed under the name of casein. The use of this term is rather confusing. In many modern books it does not appear at all in connection with the vegetable kingdom, but is replaced by legumen. Liebig regarded this nitrogenous constituent of the leguminous seeds, almonds, etc., as identical with the casein of milk, and it was a pupil and friend of Liebig's, the late Prince Consort, who devised and originally supervised this graphic method of displaying the chemistry of food. I will not here discuss the vexed question of whether the analysis of Liebig, identifying legumin with casein, or rather those of Dumas and Cahors, who state that the vegetable casein is not of the same composition as animal casein, are correct. The following figures display my justification for thus lightly treating the discussion. The first column shows the results of Dumas for animal casein: carbon 53-7, hydrogen 7-2, nitrogen 16-6, oxygen and sulfur 22-5. The second, those of Dumas and Cahors for legumin: carbon 50-50, hydrogen 6-78, nitrogen 18-17, oxygen and sulfur 24-55. The third, those of Jones for the same: carbon 55-05, hydrogen 7-59, nitrogen 15-89, oxygen and sulfur 21-47. The fourth, those of Rocheletter: carbon 56-24, hydrogen 7-97, nitrogen 15-83, oxygen and sulfur 19-96. All as quoted by laymen. Here it will be seen that the differences upon which Dumas and Cahors base their supposed refutation of the identity of the animal with the vegetable principle are much smaller than the differences between the results of different analyses of the latter. These differences, I suspect, are all due to the difficulty of isolating the substances in question, especially of the vegetable substance, which is so intimately mixed with the starch, etc., in its natural condition, that complete separation is of questionable possibility. The difficulty, or impossibility, of driving off all the adhering water without removing the combined elements of water is a further source of discrepancy. This will be understood by the following description of the method of separation as given by Miller, Elements of Chemistry, Volume 3. Legumin is usually extracted from peas or from almonds by digesting the pulp of the crushed seeds in warm water for 2 or 3 hours. The undissolved portion is strained off by means of linen, and the turbid liquid allowed to deposit the starch which it holds in suspension. It is then filtered and mixed with dilute acetic acid. A white flocculent precipitate is thus formed, which must be collected on a filter and washed. This is but a mechanical process, and its liability to variation in result may be learned by anybody who will repeat it, or who has separated the gluten of flour by similar treatment. Practically regarded in relation to our present subject, casein and legumin may be considered as the same. Their nutritive values are equal and exceptionally high, supposing they can be digested and assimilated. One is the most difficult of digestion of the nitrogenous constituents of vegetable food, and the other enjoys the same distinction among those of animal food. Both primarily exist in a soluble form. Both are rendered solid and insoluble in water by the action of acids. Both are precipitated as occurred by rennet. And both are rendered soluble after precipitation, or are retained in their original soluble form by the action of alkalis. They nearly resemble in flavor, and John Chinaman makes actual cheese from peas and beans. Peas pudding hot, peas pudding cold, peas pudding in the pot 9 days old. I leave it to Mr. Clodd, the historical problem of determining whether this notable couplet is of Semitic, Aryan, Neolithic, or Paleolithic origin. Regarded from my point of view, it expresses a culinary and chemical principle of some importance, and indicates an ancient practice that is worthy of revival. I have lately made some experiments on the ensilage of human food, whereby the cellular tissue of the vegetable may be gradually subjected to that breaking up of fiber already described. One of the curious achievements of chemical metamorphosis that is often quoted as a matter for wonderment is the conversion of old rags into sugar by treating them with acid. The wonderment of this is diminished, and its interest increased, when we remember that the cellulose or woody fiber of which the rags are composed has the same composition as starch, and thus its conversion into sugar corresponds to the everyday proceedings described in Chapter 11. All that I have read and seen in connection with the recent ensilage experiments on cattle fodder indicates that it is a process of slow vegetable cookery, a digesting or maceration of fibrous vegetables in their own juices, which loosens the fibers, renders it softer and more digestible, and not only does this, but to some extent converts it into dextrin and sugar. I hereby recommend those gentlemen who have ensilage pits, and are sufficiently enterprising to try bold experiments, to water the fodder, as it is being packed down, with dilute hydrochloric acid, or acetic acid, which, if I am not deluded by plausible theory, will materially increase the sugar-forming action of the ensilage. The acid, if not oversupplied, will find ammonia and other bases with which to neutralize itself. Such ensilage will correspond to that which occurs when we gather Jersey or other superlatively fine pears in autumn as soon as they are full grown. They are then hard, woody, and acid, quite unfit for food. But by simply storing them for a month, or 2 or 3, they become lusciously tender and sweet. The woody fibers are converted into sugar, the acid neutralized, and all this by simply fulfilling the conditions of ensilage, viz., close packing of the fiber, exclusion of air by the thick rind of the fruit, plus the other condition which I have just suggested, viz., the diffusion of acid among well-packed fibers of the ensilage material. In my experiments on the ensilage of human food, I have encountered the same difficulty as that which has troubled graziers in their experiments, viz., that small-scale results do not fairly represent those obtained with large quantities. There is besides this another element of imperfection in my experiments respecting which I am bound to be candid to my readers, viz., that the idea of thus extending the principle was suggested in the course of writing this series, and therefore a sufficient time has not yet elapsed to enable me, with much other occupation, to do practical justice to the investigation. I find that oatmeal porridge is greatly improved by being made some days before it is required, then stored in a closed jar, brought forth and heated for use. The change effected is just that which theoretically may be expected, viz., a softening of the fibrous material and a sweetening due to the formation of sugar. This sweetening I observed many years ago in some gruel that was partly eaten one night and left standing until next morning, when I thought it tasted sweeter. But to be assured of this, I had it warmed again 2 nights afterwards, so that it might be tasted under the same conditions of temperature, palate, etc., as at first. This sweetness was still more distinct, and the experiment was carried no further. I have lately learned that my ensilage notion is not absolutely new. A friend who read my Cantor lectures tells me that he has long been accustomed to have his porridge made some days before eating it, then having it warmed up when required. He finds the result more digestible than newly made porridge. The classical 9-days-old peas pudding is a similar anticipation, and I find, rather curiously, that 9 days is about the limit to which it may be practically kept in a cool place before mildew, moldiness, is sufficiently established to spoil the pudding. I have not yet tried a barrel full of peas pudding or moistened peas meal, closely covered and powerfully pressed down, but hope to do so. Besides these, we have a notable example of ensilage in sauerkraut, a foreign luxury that John Bull, with his usual blindness, denounces as a matter of course, horrid stuff, beastly mess, and such like expressions I hear whenever I name it to certain persons. Who are these persons? Simply English men and English women who have never seen, never tasted, and know nothing whatever of what they denounce so violently, in spite of the fact that it is a staple article of food among millions of highly intelligent people. Common sense, to say nothing of that highest result of true scientific training, the faculty of suspending judgment until the arrival of knowledge, should suggest that some degree of investigation should precede the denunciation. In the cases of the sauerkraut and the ripening pear, there is acid at work upon the fiber, which, as I have before stated, assists in the conversion of this indigestible constituent into soluble and digestible dextrin and sugar. The demand for the solution of the vegetable casein, or legumin, which has such high nutritive value and is so abundant in peas, etc., is of the opposite kind. Acids solidify and harden casein, alkalize, soften, and dissolve it. Therefore, the chemical agent suggested as a suitable aid in the ensilage or slow cookery, or the boiling or rapid cookery of leguminous food, is such an alkali as may be wholesome and compatible with the demands for nutrition. The analysis of peas, beans, lentils, etc., show a deficiency of potash salts as compared with the quantity of nitrogenous nutriment they contain. Therefore, I propose, as in the case of cheese food, that we should add this potash in the convenient and safe form of bicarbonate, not merely add it to the water in which the vegetables may be boiled and which water is thrown away, as in the common practice of adding soda when boiling greens, but add the potash to the actual peas porridge, peas pudding, lentil soup, etc., and treat it as part of the food as well as an adjunct to the cookery. This is especially required when we use dried peas, dried beans of any kind, such as haricots, dried lentils, etc. I find that taking the ordinary yellow split peas and boiling them in a weak solution of bicarbonate of potash for 2 or 3 hours, a partial solution of the casein is effected, producing peas pudding, or peas porridge, or puree, according to the quantity of water used, which is softer and more gelid than that which is obtained by similarly boiling without the potash. The undissolved portion evidently consists of the fibrous tissue of the peas, the gelatinous or undissolved portion being the starch, with more or less of casein. I say more or less, because at present I have not been able to determine whether or not the casein is all rendered soluble. The flavor of the clear pea soup which I obtained by filtering through flannel shows that some of the casein is dissolved. This is further demonstrated by adding an acid to the clear solution, which at once precipitates the dissolved casein. The filtered pea soup sets to a stiff jelly on cooling. and promises to be a special food of some value. But for the reasons above stated, I am not yet able to speak positively as to its quantitative value. The experience of any one person is not sufficient for this. The question being, not whether it contains nutritive material, this is unquestionable, but whether it is easily digested and assimilated. As we all know, a food of this kind may agree with some persons and not with others, i.e., it may be digested and assimilated with these, or with difficulty, according to personal idiosyncrasies. The cheesy character of the abundant precipitate which I obtain by acidulating this solution is very interesting and instructive, regarded from a chemical point of view. The solubility of the casein is increased by soaking the peas for some hours, or better still, a few days, in the solution of bicarbonate of potash. Another question is opened by these experiments, vis-a-vis what is the character and the value of the fibrous solid matter remaining behind after the filtering out of the clear pea soup. Has the alkali acted in an opposite manner to the acid in the ripening pear? Is it merely a fibrous refuse only fit for pig food, or is it deserving of further attention in the kitchen? Should it be treated with dilute acid, say a little vinegar, to break up the fiber, and thereby be made into good porridge? Other questions crop up here as they have been cropping continually since I committed myself to the writing of these papers, and so abundantly that if I could afford to set up a special laboratory and endow it with a staff of assistants, there would be some years' work for myself and staff before I could answer them exhaustively, and doubtless the answers would suggest new questions, and so on ad infinitum. I state this in apology for the merely suggestive crudity of many of the ideas that I have thrown out. Before leaving the subject of peas, I must here repeat a practical suggestion that I published in the Birmingham Journal about 20 years ago, vis-a-vis that the water in which green peas are boiled should not be thrown away. It contains much of the saline constituents of the peas, some soluble casein, and has a fine flavor, the very essence of the peas. If to this, as it comes out of the saucepan, be added a little stock, or some of Liebig's extract, a delicious soup is at once produced, requiring nothing more than ordinary seasoning. With care, it may form a clear soup, such as just now is in fashion among the fastidious. But prepared however roughly, it is very economical, wholesome, and appetizing soup, and costs a minimum of trouble. I must here add a few words in advocacy of the further adoption in this country of the French practice of using as pottage the water in which vegetables generally, excepting potatoes, have been boiled. When we boil cabbages, turnips, carrots, etc., we dissolve out of them a very large proportion of their saline constituents, salts which are absolutely necessary for the maintenance of health, salts without which we become victims of gout, rheumatism, lumbago, neuralgia, gravel, and all the ills that human flesh with a lithic acid diathesis is heir to, i.e. about the most painful series of all its inheritances. The potash of these salts existing therein in combination with organic acids is separated from these acids by organic combustion, and is then and there presented to the baneful lithic acid of the blood and tissues, the stony torture particles of which it converts into soluble lithate of potash, and then enables them to be carried out of the system. I know not which of the fathers of the church invented fast day and soup maigre, but could almost suppose that he was a scientific monk, a profound alchemist like Basil Valentine, who in his seeking for the aurum potable, the elixir of life, had learned the beneficent action of organic potash salts on the blood, and therefore used the authority of the church to enforce their frequent use among the faithful. The above remarks, when published in Knowledge, invoked much correspondence, including many inquiries for further information concerning the salts that should be contained in our food, and in what other form they might be obtained. I therefore add the following, especially as I can speak from practical experience of the miseries that may be escaped by understanding and applying it. I inherit what is called a lithic acid diathesis. My father and his brothers were martyrs to rheumatic gout, and died early in consequence. I had a premonitory attack of gout at the age of 25, and other warning systems at other times, but have kept the enemy at bay during 40 years by simply understanding that this lithic acid, stony acid, combines with potash, forming thus a soluble salt, which is safely excreted. Otherwise, it is deposited here or there, producing gout, rheumatism, stone, gravel, and other dreadfully painful diseases, which are practically incurable when the deposit is fairly established. By effecting the above-named combination in the blood, the deposition is prevented. The potash required for the purpose exists in several conditions. First, in its uncombined state as caustic potash. This is poison for the simple reason that it combines so vigorously with organic matter that it would decompose the digestive organs themselves if presented to them. The lower carbonate is less caustic, the bicarbonate nearly but not quite neutral. Even this, however, should not be taken as food, because it is capable of combining with the acid constituents of the gastric juice. The proper compounds to use are those which correspond to the salts existing in the juices of vegetables and flesh, vis-a-vis compounds of potash with organic acids, such as tartaric acid, which forms the potash salt of the grape, such as citric acid, with which potash is combined in lemons and oranges, malic acid, with which it is combined in apples and many other fruits, the natural acids of vegetables generally, lactic acid in milk, etc. All these acids and many others of similar origin are composed of carbon, oxygen, and hydrogen, held together with such feeble affinity that they are easily dissociated or decomposed by heat. This may be shown by heating some cream of tartar or tartaric acid on a strip of metal or glass. It will become carbonized to a cinder, like other organic matter. If the heat is raised sufficiently, this cinder will burn away to carbonic acid and water in the case of the pure acid, or will leave carbonate of potash if the cream of tartar or other potash salt is thus burned. Unless I am mistaken, this represents violently what occurs gradually and mildly in the human body, which is in a continuous state of slow combustion so long as it is alive. The organic acids of the potash salts suffer slow combustion, give off their excess of carbonic acid and water to be breathed out, evaporated, and ejected, leaving behind their potash, which combines with the otherwise stony lithic acid just when and where it comes into separate existence by the organic actions which affect the above described slow combustion. If we take potash in combination with a mineral acid, such as the sulfuric, nitric, or hydrochloric, no such decomposition is possible. The bonds uniting the elements of the mineral acid are too strong to be sundered by the mild chemistry of the living body, and the mineral acid, if separated from its potash base, would be most mischievous as it precipitates the lithic acid in its worst form. For this reason, all free mineral acids are poisons to those who have a lithic acid diathesis. They may even create it where it did not previously exist. Hence the iniquity of cheapening the manufacture of lemonade, ginger beer, etc., by using dilute sulfuric or hydrochloric acid as a substitute for citric or tartaric acid. I shall presently come to the cookery of wines, and have something to say about the mineral acids used in producing the choicier qualities of some very dry, high-priced samples, which, according to my view of the subject, have caused the operations of lithotomy and lithotrity to be included among the luxuries of the rich. It should be understood that when I recommend the use of bicarbonate of potash for the solution of casein, all these principles were kept in view, including the objection to the bicarbonate itself. In the case of the cheese, the quantity recommended was based on an estimate of the quantity of lactic acid existing in the cheese and capable of leaving the casein to go over to the potash. In the case of the peas, the quantity is difficult to estimate, owing to its variability. The more correct determination of such quantities is among the objects of further research to which I have before alluded. Speaking generally, it is not to the laboratory of the chemist that we should go for our potash salts, but to the laboratory of nature, and more especially to that of the vegetable kingdom. They exist in the green parts of all vegetables. This is illustrated by the manufacture of commercial potash from the ashes of the twigs and leaves of timber trees. The more succulent the vegetable, the greater the quantity of potash it contains, though there are some minor exceptions to this. As I have already stated, we extract and waste a considerable proportion of these salts when we boil vegetables and throw away the pottage, which our wiser and more thrifty neighbors add to their everyday menu. When we eat raw vegetables, as in salads, we obtain all their potash. Fruits generally contain important quantities of potash salts, and it is upon these especially that the possible victims of lithic acid should rely. Lemons and grapes contain them most abundantly. Those who cannot afford to buy these articles of daily food may use cream of tartar, which, when genuine, is the natural salt of the grape, thrown down in the manner I shall describe when on the subject of the cookery of wines. At the risk of being accused of presumption, I must here protest, as a chemist, against one of the fallacies of the faculty, or of certain members of the faculty, vis-a-vis that of indiscriminately prohibiting to gouty and rheumatic patients the use of acids or anything having an acid taste. This has probably arisen from experiences of the fact that mineral acids do serious mischief, and that alkaline carbonate of potash affords relief. The difference between the organic acids which are decomposed in the manner I have described, and the fixed composition of the mineral acids, does not appear to have been sufficiently studied by those who prohibit fruit and vegetables on account of their acidity. It must never be forgotten that nearly all the organic compounds of potash, as they exist in vegetables and fruit, are acid. It may be desirable in some cases to add a little bicarbonate of potash to neutralize this excess of acid and increase the potash supply. I have found it advantageous to throw a half saltspoonful of this into a tumbler of water containing the juice of a lemon, and have even added it to stewed or baked rhubarb and gooseberries. In these it froths like whipped cream, and diminishes the demand for sugar, an excess of which appears to be mischievous to those who require much potash. I must conclude this sermon on the potash text by adding that it is quite possible to take an excess of this solvent. Such excess is depressing. Its action is what is called lowering. I will not venture upon an explanation of the rationale of this lowering, or discuss the question of whether or not the blood is made watery, as sometimes stated. Intimately connected with this part of my subject is another vegetable principle that I have not yet named. This is vegetable jelly, or pectin, the jelly of fruits of turnips, carrots, parsnips, etc. Fremy has named it pectose. Like the saline juices of meat, it is very little changed by cookery. An acid may be separated from it which has been named pectic acid, the properties and artificial compounds of which appear to me to suggest the theory that the natural jelly of fruits largely consists of compounds of this acid with potash or soda or lime. We all know the appearance and flavor of currant jelly, apple jelly, etc., which are composed of natural vegetable jelly plus sugar. The separation of these jellies is an operation of cookery, and one that deserves more attention than it receives. I shall never forget the rahat lakum prepared for the Sultana, which I once had the privilege of eating in the kitchen of Seraglio of Stamboul, where it was presented to me by His Excellency the Grand Confectioner as a sample of his masterpiece. Its basis was the pure pectose of many fruits. This inspicisated juices of grapes, peaches, pineapples, and I know not what others. The sherbet was similar, but liquid. Well may they obey the prophet and abstain from the grosser concoctions that we call wine, when such ambrosial nectar as this is supplied in its place. It is to imperial Tokay as Tokay is to table beer. I tasted many choice confections there, and when I find myself defending the Turk against his many enemies, my conscience sometimes asks whether my politics have been influenced by the remembrance of that visit. The lumps of delight sold by our confectioners are imitations made of flavored gelatin. Similar substitutes are sold in Constantinople, the same as regards the sherbet. I conclude this part of my subject by re-echoing Mr. Gladstone's advocacy of the extension of fruit culture. We shamefully neglect the best of all food in eating and drinking so little fruit. As regards cooked fruit, I say jam for the million, jelly for the luxurious, and juice for all. With these in abundance, the abolition of alcoholic drinks will follow as a necessary result of natural nausea. I may add that besides the letters asking for further information here given, I have since received several others from readers who have adopted the diet above prescribed with good practical results. I have further learned that vegetarians are remarkably free from lithic acid troubles above named, and that many who were sufferers before they became vegetarians have subsequently escaped. The testimony of a large number is demanded in such subjects, as individual examples may depend upon individual peculiarities of constitution. End of section 14.